Scalars, physical quantities completely described by a numerical value alone and added according to ordinary rules of algebra are called scalars. For example, time, mass, temperature, etc. Vectors, the physical quantities which have magnitude and direction and which can be added according to the vector addition rule are called vector quantities. For example, displacement, velocity, force, etc. Let us now consider the representation of vectors. Vectors are represented by a directed line segment. In the figure, there are two velocity vectors, 1 meter per second and 2.5 meter per second. Both are acting to the right direction. There is another 1 meter per second velocity vector which is acting upward. And finally, 3 meter per second velocity vector acting in a general direction. As it is clear from the figure, all these velocity vectors are represented by directed line segments. In the representation of vectors, the front end carrying the arrow is called the head and the rear end is called the tail. In the figure, first velocity vector is acting from A to B, second velocity vector is acting from B to C, and the resultant velocity vector is acting from A to C. The vectors are denoted by putting an arrow over the symbols representing them. Thus we write vector AB, vector BC, etc. Sometimes a vector is represented by a single letter, such as write vector V, vector F, etc. Let us now consider the condition for equality of vectors. Two vectors representing two values of the same physical quantity are called equal if their magnitudes and directions are same. In the figure, we have two velocity vectors, vector v1 and vector v2. Both have same magnitude equal to 2.5 meter per second. They are acting towards right. Since both have same magnitude and direction, they are equal vectors. Therefore, we can say vector v1 is equal to vector v2. A parallel translation of a vector does not bring about any change in it. To explain this idea, let us consider an example. In the figure, we have a velocity vector 2.5 meter per second acting towards right. If we displace this vector up, down, forward or backward parallel to itself, then the velocity vector remains the same. When we consider a physical quantity, there is an important point to remember. If a physical quantity has magnitude as well as direction, but does not add up according to the vector addition rule, it will not be called a vector quantity. For example, electric current in a wire has both magnitude and direction, but there is no meaning of vector addition rule there. Thus, electric current is not a vector quantity.